Hello everyone. So in this video we continue with chapter 16, Integral Calculus 2. Specifically section 16.2, first order linear differential equations, use of the integrating factor. So a first order differential equation has only the first derivative in the equation. A differential equation is linear when both the derivative of y and y appear only to the first power. The standard form for the first order linear differential equation is dy over dx, or derivative of y in terms of x, plus a function p of x times y is equal to another function q of x. It can also be written using y prime. We will now look at a method of solving first order linear differential equations with this form. We will approach the solution using three cases of increasing complexity. So let's take a look at case 1. P of x is a constant, so we can write P of x as P, and Q of x is equal to 0. The equation has constant coefficients and is homogeneous. So notice that we write it as derivative of y plus P times y is equal to 0. And then we can easily rearrange this into dy over y is equal to minus P dx. And this leads to a familiar solution with direct integration. So we get natural logarithm of the absolute value of y is equal to minus px plus c. And from there, the general solution, y equals c times e to the power of minus px. Case 2 is where p of x is still a constant. So we can write p of x equal to p. And now q of x is not equal to 0. So this equation has constant coefficients, but is now non-homogeneous. And it would be in this form. Dy dx plus p times y is equal to q of x. Again, p is a constant, but it is not possible to separate the variables. However, the left-hand side is a truncated part of the derivative of a product. And so we can find another function u that enables us to write the left-hand side as derivative of y times u plus y times the derivative of u. So notice that this is just the expansion of the product rule. That's why you see that it's equivalent to this, right? The derivative of y times u. And this is only possible if u is equal to e Euler's number to the power of px. Because if we do the derivative of y times e to the power of px, you're going to get derivative of y times e to the power of px plus y times the derivative of e to the power of px, which is derivative of y times e to the power of px plus y times p times e to the power of px. So that means that if we multiply both sides of the differential equation by e to the power of px, which is called the integrating factor or an integrating factor. So notice that here we multiply both sides of the equation by e to the power of px. So from here, we're going to get this expression on the left-hand side, e to the power of px derivative of y plus p times e to the power of px times y is equal to e to the power of px times q. And then this is just going to be the derivative of e to the power of px times y, right? Because this is the product rule. And then this would equal, again, e to the power of px times q of x. Upon integrating, we're going to get this on the left-hand side. And on the right-hand side, we have to integrate for e to the power of px times qx dx plus a constant c we're going to get, right? So this expression can be integrated using familiar methods of integration, which finally leads to a general solution. So you can memorize this formula, but only after you understand the concept. That would be through a few examples. So this is a general solution. Y equals e to the minus px times the integral of e to the px times qx dx plus c times e to the power of negative px. So now let's take a look at example 16.18, and it says, find all the solutions to derivative of y plus 5y is equal to 3x. So let's recall that the integrating factor is of the form e to the power of p times x. So p here is 5. So the integrating factor is going to be e to the power of 5 times x. So we multiply both sides of the equation by the integrating factor. We should get e to the power of 5x times the derivative of y plus e to the power of 5x times 5y is equal to e to the power of 5x times 3x. But notice that what's on the left-hand side is simply the product rule of the derivative of e to the power of 5x times y. And on the right-hand side, it stays the same, e to the power of 5x times 3x. But then we can rearrange, and we're going to get derivative of e to the power of 5x times y is equal to e to the power of 5x times 3x dx. Now we can integrate both sides. So on the left-hand side, because it's the antiderivative of the derivative, we just get e to the power of 5x times y is equal to, and then on the right-hand side, you're going to have to do integration by parts, but I leave that to you as a practice. You should get 3/5 x times e to the power of 5x plus, or minus, sorry, 3/25 times e to the power of 5x plus a constant c. Now we divide both sides by e to the power of 5x, and we get y equals 3/5 x minus 3/25 plus constant c times e to the power of minus 5x. So now we're going to take a look at case 3, where p of x is not a constant and q of x is not equal to 0. So the equation has variable coefficients and is non-homogeneous. So it would be in this form. First, the derivative of y plus a function p of x times y, and this is equal to another function q of x. So before we look at this case, we need a couple of facts. First, from the fundamental theorem of calculus that we covered in chapter 14, we know that the derivative of an integral is going to be the function contained within the integral, so p of x. Then, taking a look at the chain rule, if we do the derivative of Euler's number to the power of the integral of p of x dx, that's going to equal, and this is because of the rules related to Euler's number, the derivative is going to be e to the power of the integral of p of x dx times the derivative of the inside, applying the chain rule. And it's going to be the derivative of the integral of p of x dx, which is going to finally give us p of x times e to the power of the integral of p of x dx. So these are two facts that we were going to use, and this is labeled 1 and 2. Now this looks a lot more complicated than it is in practice, and you'll see in the next example. Now let's consider the general differential equation from case 3, which is this one again. First thing to do is multiply both sides by the integrating factor, which is going to be e to the power of the integral of p of x dx. So notice that here, both sides of the equation were multiplied by the integrating factor. So on the left-hand side, you're going to be left with this, the equivalent of the derivative of y times e to the power of the integral of p of x dx, because it is simply the product rule, as is proven here. And the right-hand side stays as e to the power of the integral of p of x dx times q of x. So then, by integration, we're going to get this expression on the left, and on the right-hand side, we're going to integrate this, right? E to the power of the integral of p of x dx times q of x dx, plus a constant c that we need. And then this is a general solution in a formula that leads to y is equal to e to the minus integral of p of x dx times the integral of the right-hand side plus a constant c times e to the power of negative integral of p of x dx. So this is the same formula that we found for case 2. So now let's go to an example. So now let's do example 16.19. And it says, find all solutions to the differential equation 2x times the derivative of y plus 8y is equal to 5x to the power 4. Now, the first thing we need to do is to make sure that we have the differential equation in the form derivative of y plus p of x times y is equal to q of x. So notice that here we have to divide both sides by 2x. And if we do that, we're going to get dy over dx plus 4 over x times y is equal to 5/2 x cubed. Then we can identify p of x, and p of x is 4 over x. Then we need to do the integral of p of x dx, which is going to be the integral of 4 over x dx, and this is going to equal 4 times the natural logarithm of the absolute value of x, but this is equal to natural logarithm of x to the 4 using the properties of logarithms. And we don't need the absolute value because it's to the power of an even number, 4. Okay, now we need to find out what the integrating factor is. And the integrating factor is in the form e to the power of the integral of p of x dx. So this is going to equal e to the power of the natural logarithm of x to the 4, which is equal simply to x to the 4. So that's the integrating factor. So now we need to multiply both sides of the equation by the integrating factor. So we're going to get x to the 4 times derivative of y dx plus x to the 4 times 4 over x times y is equal to x to the power 4 times 5/2 x to the power of 3. And then this is going to give us x to the 4 derivative of y plus 4x cubed times y is equal to 5/2 x to the power of 7. So notice that here we have the product rule of the derivative of x to the 4 times y. So we can rewrite this as derivative of x to the 4 times y on the left-hand side is equal to 5/2 x to the 7. So again, we integrate both sides. And on the left-hand side, we're going to get x to the 4 times y is equal to 5 over 16 x to the 8 plus an arbitrary constant c. And then finally, we divide both sides by x to the 4. So y is equal to 5 over 16 x to the 4 plus a constant c times x to the minus 4. So notice that we would have gotten the same answer if we had applied the formula, the final formula. And in this case, it would have been y is equal to the integrating factor with a negative exponent. So that would be x to the minus 4 times the integral of the right-hand side, which would have been 5/2 x to the 7 dx, which I forgot to write over here, plus a constant c times x to the minus 4. So let's continue with example 16.20, and it says find the initial value solution of the derivative of y plus y times tangent of x is equal to cosine squared of x, where y of 0 is equal to 2. So first of all, let's rewrite this as dy dx plus tangent of x times y is equal to cosine squared of x. So p of x is tangent. P of x is tangent of x. Then the integral of p of x dx is the integral of tangent of x dx, which is the natural logarithm of secant of x. So the integrating factor is going to be e to the power of the natural logarithm of secant of x, which is simply secant of x. So now we multiply both sides of the equation by secant of x, and we have secant of x times the derivative of y plus secant of x times tangent of x times y is equal to secant of x times cosine squared of x. So on the left-hand side, what we have really is, again, the product rule. In this case, for secant of x times y, derivative of secant of x times y. So let's write that here. Dx of y times secant of x is equal to cosine of x, right? Because secant is 1 over cosine. So now we can integrate both sides of the equation. And let's not forget dx here. And we're going to get y times secant of x is equal to the sine of x plus a constant c. Divide both sides by secant of x. We're going to get y is equal to sine of x plus c divided by 1 over cosine, which is the same as multiplying by cosine of x. Okay, since this is an initial value problem, we need to plug in 0 for x and 2 for y in order to solve for c. So we know that y of 0 is equal to 2, as I indicated up here. So that means that 2 is equal to the sine of 0 plus c times the cosine of 0. So this is going to be 2 is equal to c, right? Because sine of 0 is 0 and cosine of 0 is 1. So that means that we have the initial value solution of the differential equation. It's going to be y equals sine of x plus 2 times cosine of x. So now let's take a look at example 16.21. And it says, find the solution to derivative of y in terms of t is equal to 2t over 1 plus t squared times y plus 2 over 1 plus t squared, where we have the initial value y of 0 is equal to 0.4. So the first thing we need to do is rearrange this, and it's going to be dy dt minus 2t over 1 plus t squared is equal to 2 over 1 plus t squared. So the first thing we need to do is find the integral of p of x, right? So that's going to be the integral of, and here we have to be careful because it's negative 2t over 1 plus t squared. And this is going to give us negative natural logarithm of 1 plus t squared, or natural logarithm of 1 plus t squared to the negative 1. So the integrating factor, which is in the form of e to the power of the integral of p of x dx, is going to be e to the power of the natural logarithm of 1 plus t squared to the negative 1, which is simply going to be 1 over 1 plus t squared. So we would multiply both sides by the integrating factor, and then we know that on the left-hand side, we're going to be left with the derivative of y times the integrating factor. And on the right-hand side, from this expression, we would get 2 over 1 plus t squared squared. Oh, this is not dx, this is dt here. Just out of habit. But we're going to send that to multiply to the other side anyway, so let's just leave it here, dt. And next, we integrate both sides of the equation. On the left-hand side, it's easy because we're left with y times 1 over 1 plus t squared. And on the right-hand side, you would have to use the method of partial fractions, but I leave that to you as an exercise. And you would get inverse tangent of t plus t over 1 plus t squared plus a constant c. Therefore, y would equal 1 plus t squared times inverse tangent of t plus t over 1 plus t squared plus a constant c. Now don't expand this, just leave it like that. You don't really need to expand these expressions. It takes too much time. Because this is an initial value problem, we need to plug in 0 for x and 0.4 for y. But if you do that, you're going to see that everything is going to cancel out, and we're going to end up with c is equal to 0.4. So we have a particular solution, and all we have to do is substitute c for 0.4. So let's continue with example 16.22, and it's basically the same thing, solving the initial value problem for x greater than 0 for this expression to the left, which is 2x derivative of y minus y is equal to x plus 1, with the initial value y of 2 is equal to 4. So first of all, let's divide both sides by 2x, and we're going to get dy dx minus 1 over 2x times y is equal to x plus 1 divided by 2x. But I'm going to separate this expression on the right-hand side because it'll be easier to integrate if we express it as 1/2 plus 1 over 2x. So p of x is minus 1 over 2x. The integral of this would be minus 1/2 times 1 over x dx, which will give us minus 1/2 times the natural logarithm of x, and this is going to be the natural logarithm of x to the minus 1/2. So the integrating factor is in the form e to the power of the natural logarithm of x to the minus 1/2. Therefore, the integrating factor is going to be x to the minus 1/2. Or if you prefer, 1 over x to the 1/2. So we're going to multiply both sides of the equation by this. And notice that we're going to get the derivative. So this is just the inverse of the product rule, right? So we would get the derivative of x to the minus 1/2, the integrating factor, times y. And on the right-hand side, we would get 1 over 2 times x to the 1/2 plus 1 over 2x to the 3/2. So let's just bring the x over to this side and erase it from here. Now we integrate both sides, and we should get x to the minus 1/2 times y is equal to x to the 1/2 plus, or no, minus, we would get minus x to the minus 1/2 plus a constant c. Send x to the minus 1/2 to divide to the other side, or divide both sides by x to the minus 1/2. We would get then that y is equal to x minus 1 plus c times x to the 1/2. But because we have an initial value, we know that y of 2 is equal to 4. We can substitute that into the equation, and we have that 4 is equal to 2 minus 1 plus c times the square root of 2. And if we solve for c, we're going to get that c is equal to 3 over the square root of 2. So we can just substitute that here in the equation to get the particular solution. So it would be 3 over square root of 2 instead of c, and we have the solution. So on the next slide, you're going to find an application to electric circuits. So an electromotive force, usually supplied by a battery or generator, produces a potential difference of E of t volts V and a current of I of t amperes A at time t. The circuit in figure 16.6 also contains a resistor with a resistance of R ohms and an inductor with an inductance of L henries. Ohm's law gives the potential difference across the resistor as R times I. The potential difference across the inductor is L times the rate of change of the current. One of Kirchhoff's laws says that the sum of the voltage drops is equal to the supplied voltage. Thus we have this differential equation. This is a first order linear differential equation. The solution gives the current I at time t. So now let's take a look at example 16.23. And it says, suppose that in the simple circuit of figure 16.6, the resistance is 12 ohms and the inductance is 4 henries. The power supply provides a constant potential difference of 60 volts, and the switch is closed when t equals 0, so the current starts with current at time 0 equal to 0. Find A, I of t. So that would be the formula, or the equation actually. All right, so for part A, let's recall from Kirchhoff's law that the inductance L times the rate of change of the current plus the resistance times the current is equal to the potential difference, which is in volts. So now we just have to substitute some of these variables with the information from the problem. So the inductance is 4, so we can write 4, and then the rate of change of the current plus the resistance, which in this case is 12 ohms, again times the current, is equal to the potential difference, which is 60 volts. Obviously, we have to divide everything by 4, so we're going to get di dt plus 3I is equal to 15. Now the integrating factor is going to be e to the power of the integral of 3 dt, which is going to be e to the power of 3t. And if we multiply both sides of the equation, we already know that we're going to get the product rule on the left-hand side of the derivative of e to the power of 3t, which is the integrating factor, times I, which represents current. And on the right-hand side, we're going to get this is equal to 15 times e to the power of 3t. So now let's just send dt to the right-hand side, and let's erase it here on the left. Let's integrate both sides of the equation, and here we're going to get e to the power of 3t times I is equal to 5 e to the power of 3t plus a constant c. So the current I is going to equal 5 plus c times e to the minus 3t. But now, remember that we have that when time is 0, the current is 0. So we can use that fact to find the value of c. So that means that 0 is equal to 5 plus c, because Euler's number to the power of 0 is just 1. So c is equal to negative 5. Let's plug that back in here and rewrite it as 5 minus 5 times Euler's number to the power of minus 3t, which can also be written as 5 times 1 minus Euler's number to the minus 3t. So now we're ready for part B, because they ask what is the current after 1 second. So that is I of 1, which is just going to be plugging in 1 into the function. So 5 times 1 minus e to the minus 3. And that's going to give us approximately 4.75 amps. And part C, the limiting value of the current. In other words, the limit as t tends to infinity for 5 times 1 minus e to the minus 3t. Now this is going to tend to 0 because it's an exponential function. 1 minus 0 is 1, 1 times 5 is 5. So it's going to be 5 amps. Okay, so now let's take a look at example 16.24. And it says, suppose that in the circuit in figure 16.6, the resistance and inductance remain constant. So that means that the resistance is still equal to 12 and the inductance L is still equal to 4. A generator produces a variable potential difference of E of t is equal to 120 sine of 60t volts, and the switch is closed when t equals 0, so the current starts with I of 0 equals 0 amps. Find I of t. This is very similar to the previous problem, except that they change the potential difference. So let's recall that L times rate of change of the current, where L is the inductance, right? Plus the resistance times the current is equal to the potential difference. So substituting the information in the formula, we get 4 times rate of change of the current plus 12 times the current, and this is now equal to 120 sine of 60t. We divide both sides by 4, and we're going to get di dt plus 3 times the current is equal to 30 sine of 60t. Multiply both sides of the equation by the integrating factor, which is e to the 3t as we found before. And we know that on the left-hand side, we're going to get the derivative of e to the power of 3t times I, and this is going to equal e to the power of 3t times 30 sine of 60t dt. So now we can integrate both sides, and let's continue here. We're going to get on the left-hand side e to the power of 3t times I, and on the right-hand side, as practice, you're going to do the method of integration by parts, and then you should get an expression that looks like this: e to the power of 3t times 10 sine of 60t divided by 401 minus, and I'll continue below, 200 cosine of 60t over 401 plus c. So we can simplify this into an expression that looks like this. I is equal to 10 over 401 of sine of 60t minus 20 cosine of 60t plus c times Euler's number to the minus 3t. And then, since we know that the current at time 0 is 0 amps, we can plug these values into the formula or the equation, and we're going to get that C is equal to 20 over 401. And then finally, we can rewrite the whole equation as I equals 10 over 401 times sine of 60t minus 20 cosine of 60t plus 2 e to the minus 3t. So now we're going to look at an application to mixture solutions. And it's going to be the last example on the video, 16.25. And it says, a tank contains 50 liters of a solution composed of 90% water and 10% hydrochloric acid. a second solution containing 50% water and 50% hydrochloric acid is being poured into the tank at a rate of 4 liters per minute. At the same time, the tank is being drained at a rate of 5 liters per minute. Part A. So the hardest part of these problems with mixture solutions is determining the equation. But let's say that we let y be the liters of acid. In the tank at any time t. Now we know that since the acid is 10% of the solution in the tank, that means that y is equal to 5 when t is equal to 0. Then we know the tank is losing 1 liter per minute of solution. Why? Well, because it's being drained at 5 liters per minute, but the other solution is being poured at 4 liters per minute. So it's losing 1 liter per minute of solution. That means that it's losing 50 minus t liters of solution per minute. Therefore, the amount of acid it's losing would be given by 5 over 50 minus t times y. At the same time, it's gaining 2 liters of acid. So this would be minus liters, this would be plus liters. Why 2 liters of acid every minute? Because the 4 liters that are being poured into the tank are 50% acid. So that would be 2 liters of acid. Okay, so that means that we can set up a differential equation in the form rate of change of y is equal to 2 minus 5 over 50 minus t times y. We can rearrange this and write it as dy dt plus 5 over 50 minus t, this is a minus here, minus t times y is equal to 2. So now it's just a matter of solving for this differential equation. I leave that to you as practice. You should get an answer of y equals 50 minus t over 2 minus 20 times 50 minus t over 50 squared. And then for part B, it says, how much acid will there be in the tank after 10 minutes? So that's just plugging in 10 into the equation. So you should get y is more or less 13.45 liters.